Hello. 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 Okay. Reply something. 感动自己，感动他人。嗨。嗨。Oh, yeah. Somebody here. Okay. Okay. Da, 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 da. Dun, dun, dun. Dun, 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 dun. I will start very soon. I will start very soon. Okay. Okay. Monday. Monday, Friday, Monday, Tuesday, Monday, Tuesday, Wednesday, Thursday. Yeah. Sorry. Oh my God. Sorry. Hey, wait a moment. Hey, hi, Mandy. Can you hear me?
Yeah, I can hear you. I heard
Okay.
that song too.
Oh, sorry.
It's okay.
Okay. Since only you here. Okay. We
Um,
can start.
yeah, there's like a test today, so I thought that most people wouldn't be here.
Okay.
Yeah.
Okay. So today's class is complex but easy. Complex is because we will talk about the Fourier transform. Easy is that for this lab, we don't need to understand the details of Fourier transform. We just want to be familiar with Fourier transform and to learn what's their meaning. So, okay. Fourier transform actually it's about the Fourier with representation. And since you know, in our reality, if we observe a curve or a wave like this, this form this formation is the time representation of the singular. It's just a wave. However, for the Fourier representation, we will observe the power distribution on the Fourier domain. For example, like this. Like this. Here, I have defined a sinusoid function, a sine function. Oh, sorry, wait a moment. Sinusoid. Wait a moment. Sinusoid function, and with the frequency, the frequency is f. F is 5 hertz. So, and if we define our sampling frequency as 8,000 hertz, and we can see the singular, the sine wave. Oh wait, I need to copy this part. Copy this part, and so this is the wave, and you can see it is rapidly changed since the frequency is 500 hertz. However, if we slow the hertz, for example, if we slow it as 20 hertz, we can see the wave. Yeah, it's like this. So this is the time representation of singulars, and it's very easy to understand because it's just this is the singular what we observed in our monitor and other device. However, Fourier representation will tell you where the power will tell you which part of Fourier domain and and the Fourier representation will tell you which part of Fourier domain the power will be located on. So, I just now, if you will learn it on Professor Zhou's class, since this is a very easy, very simple single, and in the Fourier, after the Fourier transform, you will find that the power is located at the located at the f equals 20 hertz. I mean, okay, and let me just show you. For example, here you may notice that I have defined this. So I have simple curve. Sorry, I don't mean to do this. Wait a moment, what's wrong with this? Okay, just comment this part. Comment this part and then rerun it. Yeah, and the left hand side is the time representation of signal. It's a wave with the frequency equals 20. And in the frequency domain, the x-axis is the index of frequency. You can see its frequency. This is the frequency from 0 to the 4,000 hertz. And in the for the y-axis is the magnitude. It determines the power. It determines the power corresponding to a particular frequency. So in this case, since this is a sinusoid wave with the frequency of 20 hertz, so we can see in the frequency for the frequency representation, the energy will be concentrated on 20 hertz. So so if I move it to here, you will notice that, okay, I use this. Sorry. Okay, you can see the maximum value or the maximum magnitude will be achieved when x equals around 20 hertz, and the x is corresponding to frequency, which means when frequency equals 20 hertz, we have the maximum value in this frequency domain, which means the energy is concentrated on concentrated when frequency equals to 20 hertz. So if we increase the frequency to 200 hertz, we can see yeah, like this way we can see, and you can see in the time representation, and the change, the wave is rapidly changed since the frequency is higher. And if you look into the frequency representation, and you can see here, yeah, the energy is concentrated on 200 hertz. So this is this is the frequency representation. Here I will not talk about the details of frequency representation, since I think I don't have the confidence of talking about it properly. I think Professor Zhou will give you a good representation for the Fourier transform. In this case, in this moment, I just want to tell you how to show the frequency representation. We can just use the built-in function and frequency z, and this is a built-in function, and the input variables is x, and x is the input singulus, and here the second variable is a constant value. You just fixed it as 1. And here, the third variable is the number of frequency points. So I think for this part, Professor Zhou will tell you what's the meaning. And to use this function, we must define the sampling rate. Fs is the sampling rate. Yeah, after you learn something about the sampling rate, you will learn that the sampling rate should be higher than double. The sampling rate should be higher than 2 times highest frequency, or highest single frequency. I mean, if in this case, if our single frequency f equals 200 hertz, then we should define our sampling rate fs is greater than or equal to 2 times 200 hertz, which means it should be equal to or greater than 400 hertz. Here, I just define our sampling rate as 8,000 hertz. So which means it follows this rule. Okay. And then so I think what I have told will cover the part 1. We'll cover the part 1, since part 1 is very easy. And okay, we focus on this example. Yeah. Now let's focus on this example. For example, now I define our input single x1 as no way. I define our input single x1 as a combination of 3 singuloid singles. Their frequencies are 500, 2,000, and 3,000. You can see after by showing the frequency representation like this. Okay. Wait a moment. Let me see. Okay. This figure shows the time representation. You can see it should be a complex single, since it's not a easy sinusoid singles. it's not a single or simple sinusoid signal. Um, by looking into the frequency representation, we can find their energy are located on corresponding frequencies. For example, in this case, it's they are 500, 2000, and 3000 hertz. So, this example shows we can use the frequency representation to show the energy distribution, which can help us decide whether we need that energy or to decide whether this energy is useful. If it's not used, if it is not useful, we can remove it. This technique will, or you will learn this technique in your filtering part. I mean, since you will learn it, filtering part later, not now. Okay. Now, okay. I think now you can fully finish it. You can fully finish the part one. For the part two, you will you will deal with the Yankee Doodle, right? Yankee Doodle,
Yeah.
and actually for the Yankee Doodle, you just Yankee Doodle is just a musical piece. You can download it. You can download it on the website, and you will deal with it and extract each note from the Yankee Doodle piece, and then show the frequency, show the frequency representation for each note. Okay, so actually part one is very similar to part two is very similar to part one. However, I think the most difficult part is the part three. But since you will deal with Beethoven's piece, and you should extract every note from this Beethoven's piece, and then show the frequency representation. Actually, for the Beethoven's piece, it's very easy to extract the notes, since in this piece there are only 8 notes, so you can just extract them. But the most difficult part, the most difficult piece is the circus. Means it has around 45 to 47 notes, and you need to figure out how to extract every note from this piece. This is most difficult, since for the frequency representation, it's easy to do, right? We just use that built-in function. However, how to extract the loads? I can give you some hints. For example, It's a beautiful music piece, and you can see from this 10 representation of this piece, we can find there are many notes. However, actually, for each note, I think they have the certain they have a similar pattern. You can see for each yeah, here is just a note. Here is just a note, and at the beginning it should have a sudden rise, and then there is a decay of magnitude. So you can notice that almost every note has the similar pattern. So I think this pattern will help you to extract the notes. I have counted the number of notes. I think this piece has around 45 to 46 notes. If you can follow this pattern, I think you can do this job. And then
Wait, I have a question.
okay, wait a moment.
Yeah.
Let me. Okay, please.
So I couldn't hear the music on your screen, but does each of these peaks, does it represent like a different note, or what does it represent like? Or like, does it represent like the frequency each note is at?
Yeah. Wait a moment. Let me see. Oh, you didn't hear the music. Okay.
Yeah, I couldn't hear it.
Okay, let me repeat it. Wait a moment.
Okay.
Sorry about that. Let me see how to. Oh, let me rejoin this room. I can show you the music.
Okay.
Okay.